everyone. My name is Natalie Reptak.
Andrew Nazari.
Rahul Shah.
Claire Yan.
Leah Formica. And this is designing a habitable artificial satellite for private recreational use. To begin, we will focus on the background, which concludes what the purpose of the project is. Then we will go into development of structural components and the stress analysis of said components. Then we will go further into research and then the conclusion. So for the background, the reason for this space station is to address certain demands for space tourism and for space and habitation. So these demands include overpopulation, climate change, as well as the increasing space tourism commercialization industry. So essentially this project will serve as a template for future space tourism organizations. So to create this space station, we developed and expanded on current and past space stations. So this includes the International Space Station, MER, Skylabs, as well as Salyut. For the purposes of this project, we will mostly focus on the International Space Station since it is currently in use and therefore provides a good research and resource library. We will also expand on this structural satellite using background and using new research. This new research will be the Bigelow Expandable Activity Module as well as the Rollout Solar Array ROSA, both of which have been tested on the International Space Station and have been proven to work in space. We will also have to address how the satellite functions in microgravity as well as how it shields against micrometeoroids and radiation.
After extensive research into technology of the past, present, and future, we were able to develop a sort of layout of our space station. We started by formulating what modules we were going to use and then deciding on what features would be inside. This is the assembly we came up with. We designed it in SolidWorks. SolidWorks is a computer-aided design software used frequently in the industry. We made many different parts and assembled them together into the picture you can see here. And in this image, you can see all the different parts that make up this assembly. The first piece I would like to talk about is the utility module. The utility module would be the first module sent into orbit. This is because it holds all the equipment necessary for the functioning of the spacecraft. For example, it holds the life support systems, thermal control systems, and the batteries. The next module is the prefabricated module. The prefabricated module is a very versatile tool in our design. We use it 4 times throughout the structure, as it can serve any purpose depending on what you put inside of it. It was also chosen because of its very strong rigid structure as compared to other designs. The next piece is the observation deck. The observation deck is simply a glass dome reinforced with multiple layers. The observation deck will serve as a pivot point of our space station due to the fact that it allows passengers to look out into space or back down to Earth, and it would be an incredible view unparalleled to anything passengers would have seen before. The next piece is the node. The node is critical because it serves as the hub of getting between modules. The node has 6 different connection points where modules can each connect. We have 2 nodes on our space station, one where all 6 connections are made, while the other has 4 free slots. These 4 free slots could be used later for future expansion. Next, we have the inflatable module. The inflatable module serves mostly as extra space and storage for food and other materials. The inflatable module is placed on the bottom or Earth-facing side of the satellite because it would serve as protection from micrometeoroids. And the final module is the berthing port and airlock. The berthing port is used to accept crews and supply spacecraft that would be coming to the space station. In addition, this module also has an airlock that would allow crew and passengers to make extravehicular activities. Next, we have the radiators. Radiators are simply to remove excess heat from the inside of the space station and expel it into space. Next is the solar panel. The solar panel is a rollout solar panel that will get to the size seen on the screen here. and 4 of them will supply all the electricity needed. And finally, the common berthing mechanism. The common berthing mechanism is NASA's preferred method of connecting different modules. We chose this method as it is fairly universal to different sorts of crew and resupply missions and the different capsules that would be used.
So now we'll discuss the stress analysis. So after the completion of the assembly of the spacecraft, each component was analyzed using SolidWorks simulation software to ensure that they would hold up to the pressures that would be faced in space. In order to do this, we ran a static pressure test at 1 atmosphere to simulate what the modules would be facing in orbit. And each module was simplified down to a single layer for testing. So first up, we have the inflatable module here. As you can see, the stress is centered around the middle of the module. And while this may seem worrying at first, when the deformation results were further analyzed, it was found that the pressure has a really minimal effect on the structure itself. And furthermore, the inflatable module can in fact hold up to 1,000 times greater pressure than what we have tested here. Now we also have the fabricated module and the node. Both of these performed spectacularly under the stress analysis, and there's no significant points of failure or points that need to be reinforced. To continue on, we also have the berthing module, utility module, and observation deck. The observation deck and the berthing module both also did not have any needs that needed to be addressed or any places where there was high stress. However, the utility module experienced about order of magnitude higher stress than the other modules at around 1.81 times 10 to the 7 units per meter squared. And although this is not as a factor, as they use an aluminum alloy, which is commonly used in aerospace applications, and the utility module can hold up to 27 times greater pressure than what we have tested here. And through these stress analyses, these ensure that our modules will hold up in orbit and will be safe to use against the pressures of space. So now we'll move on to the research component of our presentation and discuss some of the logistical considerations that go into the project. So for energy, right now there are 2 plausible options that can be used for energy in space. There's solar power and nuclear power. However, nuclear power has not been permitted for near-Earth human space travel, so solar power is our best option. In order to implement this, we're going to be using a derivative of NASA's ROSA solar array, which scaled up will produce about 25 kilowatts each for our station, totaling 100 kilowatts. This energy will be stored in 25 lithium-ion batteries, which have been tested and recently implemented in space. We estimate the energy usage of our station to be between 85 to 95 kilowatts. And this number was derived from looking at the ISS's current energy usage, which hovers around 100 to 110 kilowatts. And they have a lot more energy-intensive research projects, which we will not include, making our station use between 85 to 95 kilowatts of energy.
So for a propulsion system, our station will need constant reboosts and corrections in order to not only keep it in its orbit, but to make sure it can avoid micrometeorites and space debris. Space debris can travel at a velocity of 10 kilometers per second, so any damage it may do to the spacecraft would be significant. In space, there's atmospheric drag to our station. This atmospheric drag would pull our station out of its planned orbit, and we would correct this by doing reboosts from another vehicle that would be attached to our space station that would align it back to its orbit. In order to avoid micrometeorites, we would use thrusters and CMGs to alter the course of our space station. CMGs are massive steel wheels that spin at a high velocity that can store angular momentum, and that angular momentum can be used for attitude control adjustments and rotations. Given that it is in space, it is susceptible to a lot of space debris. I mentioned that we are going to use manual maneuvers, but we will also be using a combination of 2 other primary forms of shielding, one of which is the Whipple shield. The Whipple shield is the use of an aluminum wall that is a sacrificial shield, so any projectiles that smash into it hopefully break into pieces, or its impact momentum will be distributed across the wall. We will also be using radar along with the manual maneuvers. Radar can
A lot of radar systems can detect objects that are greater than 10 centimeters in diameter. And not only that, but it can track its orbit and plan its orbit. So if the space debris orbit is a couple kilometers close to the orbit of our station, our station would be given further notice and can make its manual maneuver adjustments. The final form of shielding that we would be implementing is the multi-shock shielding, which uses several thin layers of ceramic fabric that can shock projectiles to a high enough level that they either melt or evaporate on impact that would protect the integrity of our station. Moving on to the internal components, we will have a life support system so that the interior structure of our space station is hospitable to human life. We will have an air filtration system that will take carbon dioxide into ventilation systems and filter out contaminants. And in terms of obtaining oxygen, we would use water electrolysis that would break water into its components of hydrogen and oxygen. Oxygen would be vented back into the cabin air, while the hydrogen will either be vented out into space or combined with the filtered carbon dioxide to create methane and drinkable water. We will also be recycling any water on the station. Usually this is in the form of liquid waste. The liquid waste would be put through a distillation process where the water from the liquid waste would be evaporated and forced through a filtration process, making it drinkable water. In terms of waste management, we would have the crew hand compact any trash that is accumulated on board, duct tape it sealed, and stored it in bags. These bags would be put into rigid containers, and these rigid containers would be put in the inflatable module of our space station to prevent cross-contamination between waste and the passengers. Hopefully, then we can put the rigid containers in an empty supply vehicle that will return to Earth and burn in Earth's atmosphere.
Regarding emergencies, there are three main classes in space: fire, depressurization, and toxic release. Fires would be detected using smoke detectors that are linked to ventilation systems that report back to a main control system panel. This panel would then state the fire's location and cut off fans and electrical systems to that location, after which water-based foam and carbon dioxide extinguishers could be used. If these steps failed, the module would be depressurized. On the other hand, in case of unexpected depressurizations, passengers and crew would report to emergency vehicles located at the docking ports that would separate from the station and return to Earth. The last category of emergency, toxic release or ammonia leaks, requires that intermodule ventilation be shut down and passengers and crew put on oxygen masks in order to go into emergency vehicles that don't use ammonia. Meanwhile, ammonia filtration would occur, after which everyone could return to the station. Moving into launch vehicles in orbit, after some consideration, we decided to use SpaceX's Falcon 9 in order to launch the nodes and the inflatable module into orbit. For larger modules such as the prefabs, we would be using United Launch Alliance Atlas V. And these launch vehicles were chosen in order to maximize efficiency when sending all the components of the space station into their orbit at 390 to 440 kilometers above sea level. This altitude was chosen in order to minimize atmospheric drag while simultaneously keeping the station out of irradiated Van Allen belts. And finally, one of the most important components of our station is the passengers. And the first requirement for the guests would be that they pass extensive background checks in order to confirm not only their own comfort in space, but also that they wouldn't be a harm to other passengers. Regarding actual life in the station, there would be disturbances to sleep due to constant noise, which would harm passengers' overall health in addition to specifically targeting their immune system. Muscular atrophy is another prominent condition due to microgravity, though its effects can be slowed with proper exercise and dieting. Furthermore, hygiene cannot be maintained in space the same way that it is done on Earth, which should also be taken into consideration when dealing with guests. But aside from all these physical health effects, mental health is also important to consider. Due to such drastic environmental differences, there is no doubt that passengers will suffer discomfort at some point during their stay.
Okay, to conclude, we were able to create a space station that can serve as the first step towards space tourism. In addition, we looked through CAD designs and we also researched about other space stations to develop the structural layout of this space station. Then we also developed looked at stress tests, analyzing the structural layout. Through these tests, we were able to determine that there are no significant points of failure on the space station. Then, to provide a holistic view of said space station, we researched further into essential systems such as life support, propulsion, energy, as well as the well-being of passengers. And then we looked into the commercialization of such systems. For future research, we are able to determine that the detailed model would prove to be better functional, and we were able to determine that interior layout could also be addressed. In addition, mental and physical health evaluation will have to be considered, as space has not been suitable for long-term inhabitation recently. We would like to acknowledge the following people and thank them. Our mentor, Michael Higgins, for his support and aerospace expertise. Dean Rosen and Dean Antoine for their management and encouragement of this program. Head counselor Nicholas Ferreira and research coordinator Brian Bly for their help in researching. Rutgers University, Rutgers School of Engineering, and the State of New Jersey for their help in this program. Martha Terry from NASA for help with energy systems. Professor Ben Arroyo for his help in certain questions we may have about the space station. And our sponsors, Lockheed Martin, Silverline, Rubix, and others, as well as the NJGSET alumni for continuous support. Any questions?
Yeah, did you guys make those hats in SolidWorks?
Yeah, we made all of the CAD designs and put them together into the big assembly.
How long did that take you, or did you each do individual pieces?
We all collaborated to make individual parts, and we spent about a week, I'd say, in the DSB or computer lab designing each of the parts.
I think Andrew mentioned that the inflatable part of the space station, space hotel, would help protect against like the debris in space. How does that work?
So the inflatable module would actually be the part being protected. So the prefabricated modules and the solar panels would be above the inflatable module and could serve as a sort of shielding from micrometeoroids.
So what is the capacity for the station? How many people can be there?
So we designed the station to be expandable, but at the current time, it would probably hold under 10 people. But because of things like the nodes and like the ability to add more modules, we'd hope that as the station would attract more customers, we would also expand it. Any other questions?
Yeah, you.
How do you deal with space radiation?
So with the space radiation, we have a lot of, so there's a lot of layers to our space module. Even though for test analysis, we had to break it down to one level in order to make testing simplified, there would be aluminum alloy is a very common material used in the space industry, not only because it's lightweight, but its ability to protect against radiation, as well as there's other multiple layers like ceramic fiber layers, as well as other metal ores.
Additionally, the orbit itself should help prevent any issues with radiation. Since it's in a low Earth orbit, there's still some atmosphere that will help dissipate some of the radiation.
And we designed it to stay out of the Van Allen belts, which orbit at which are at higher altitudes than where our station would be located.
Any other questions? Thank you for your attention.